earlier this morning. I told her if she wanted to come back, she could. Okay, so the screencast is on batteries, and batteries are a spontaneous redox reaction. So any reaction that's spontaneous can be made into a battery. And you know it's spontaneous by looking on table J. So what we're going to do is we're going to create a battery, and the term that we're going to use is voltaic cell, and it's a type of electrochemical cell. So when you, hang on. Okay, all right, little interruption there. Okay, so what we're going to do is we're going to take a look at spontaneous reactions, and again, we can look at table J. So the two metals that we're going to use today to create this battery are copper and zinc. And then the first thing that you're going to do is, or first thing that you can do, is look at table J, and you can see which one of those chooses to be oxidized and which one of those chooses to be reduced. And right, and zinc is oxidized. So because this is higher up on chart J, this prefers to be oxidized, and then this one prefers to be reduced. So that's what we're going to be looking at, a battery that has zinc being oxidized and copper reduced. Now what happens is when something is oxidized, it's going to go from zinc 0 to zinc +2 plus 2 electrons. That's going to be losing electrons. And copper 2 plus can gain those 2 electrons, and you can go to copper 0, and that's reduced. So whenever there's an oxidation, there's also a reduction. Okay, so far so good. So if I take a piece of solid zinc and I put it into a solution that has copper ions, that's going to be, you're going to have a reaction. But what happens is the electrons go directly from the zinc to the copper in solution, and I can't direct those electrons through a wire, so they can't do any work for me. So I have to figure out a way to separate the two half reactions so that I can have the electrons travel through a wire to get back into that solution. And then along the way, I can plug in, I don't know, maybe a light bulb or something so that the electrons that go from the zinc back into the copper can do some work. Okay, so that's what a battery is. So let's erase what's on here and let's see if we can figure out how to make that battery. So we're going to start off with 2 beakers, and that's on the guided note sheet that you should have picked up. Do you have one of those, Hallie? Okay. So what we're going to do is we're going to have in each one of them a zinc sulfate solution and a copper sulfate solution. Now, the reason I use zinc sulfate and copper sulfate is if I put zinc into a solution, I don't want it to react with anything. So I'm safe if I put zinc and zinc sulfate, there's no chemical reaction. Because if I do a single replacement reaction between zinc and zinc sulfate, I get zinc and zinc sulfate. So it doesn't affect anything. And the same thing with the copper. I don't want it to react, but yet I need this solution to be an electrolytic solution, and I need that solution to be an electrolytic solution. So we also know what's going to be oxidized and what's going to be reduced. The zinc I know is going to go from zinc 0 to zinc +2. So there's my half reaction. And the copper half reaction is +2 going to copper 0. They're called oxidation and reduction. You have that already. Okay, good. So now I need to get the electrons that are lost at the zinc, and I need them to get over to the copper. Well, electrons travel really well through something called a wire. So the electrons are going to travel through the wire in that direction. But first, let me introduce you to these 2 terms here. There's these 2 terms called anode and cathode. And the copper and the zinc are metal pieces, pieces of metal that are called electrodes because they conduct electricity. So that's one electrode, and this is another electrode. Each electrode has a specific name. The anode is always where oxidation occurs, and the cathode is always where reduction occurs. And you can remember that there's a mnemonic. It's called N-ox and a red cat. Okay? Anode is where oxidation occurs. Reduction is always at the cathode. Okay, so NOx and a red cat. Now, the electrons always go from where they're lost, the oxidation or the anode, towards the cathode. So the electrons are going in that direction. Let's take a little bit of a closer look at where these electrons physically come from. If I have an atom of zinc that's in that wire, what's going to happen to that atom of zinc is it's going to give up 2 electrons. Those 2 electrons are going to travel up the wire to the other side. That makes this turn into zinc +2 ions and end up floating around in the solution because he's no longer solid zinc anymore. So what's going to happen to the size of that electrode? It's going to shrink, exactly. So that electrode shrinks over time. Now those electrons come over here, and now this is electron rich, right? So I've got all these -2 electrons. In this solution, I've got copper-2 positive ions and sulfate ions. What's going to be attracted to this negative electrode? Copper-2. Just the copper-2, the sulfate's going to be left behind. Yeah, that's okay. So the copper +2 here is going to gain those 2 electrons and turn into copper-0. So what's going to happen to the size of this electrode over time? Yeah, and it grows and grows and grows.
Is a zinc coating or just
No, with a copper
copper?
coating, more copper, because copper +2 gains the electrons that came through the wire and turns into solid copper. But we've got another problem going on here. So what happens is this zinc ion is produced, and that's a positively charged ion, yes? But things have to be electrically neutral. So what does that positive ion need? It needs a negative. But look what happened to copper. Copper just shafted its date on the other side, which was a negative ion. But how do I get that negative ion over to the other side where it's needed for the zinc? Well, we use something called a salt bridge or a U-tube, and it's filled with a salt solution. Now, salt solutions have positive and negative ions in them. You get a nice circuit of charge here. The negative electrons go in that direction. And once the negative electrons get here, I'm too negative over here. So what do I have to send back to the other side? Negative ions. So for every negative charge that comes this way, a negative ion has to go in the other direction to keep everything balanced or electrically neutral. And that's good because this sulfate is needed over here to bond with that sulfate. So negative electrons go in that direction, negative ions go in the opposite direction, and you get this circuit to keep everything balanced and neutral. And that's what your battery is. I did also throw up there that this grows and this shrinks, which we were just talking about. The wherever the oxidation is, that's the electrode that's going to decrease in size, and this is the reduction. That's where I'm going to gain that, and it's going to grow. The battery runs out or the battery dies when what happens?
When the zinc is gone.
When the zinc is gone, and then it will stop. So either I'm going to get rid of all of that zinc or all of these copper ions in solution.
only as much as submerged into the solution is lost.
Is lost, exactly. Yeah, because what's above the line is not going to be part of the reaction, and that's actually a really good point. That's why it's called a wet cell, this type of cell, and anything that's wet or part of the solution is going to be what's going to be reacting. And so that's it, and that's the battery. A rechargeable battery, what we do is this is the spontaneous or natural flow of electrons. So to recharge the battery, I would have to and flip the direction. And how do you flip the direction? Well, you take it and let's use green, I guess. We would, for a rechargeable battery, send things back in the other direction. So the anions would come this way, the electrons would go back the other way. The zinc that fell off would go back onto the electrode, so the zinc +2 ions would go back, and the copper would fall back into solution as copper 2+. Now what happens is you never get back to where you were before. You can't have 100% replacement, and that's why eventually your battery dies, even a rechargeable battery, because you never get back to where you were originally. That's what you missed. And that's why everybody, when they said that, you know, oh my gosh, you missed a big thing, it's hard to explain. But once you do it, it's not so bad. Okay, so this is a spontaneous electrochemical cell that we call a galvanic cell or a voltaic cell. Voltaic because we get volts out of it, and we can figure out exactly how many volts by using the table N in your reference tables. Good, that's it. Good.
Thank you.
Not a problem. Okay, now if I can turn this off and stop recording, we'll be good. Voltaic